Hi everyone, this is the second episode. Hi everyone, this is episode number 2 of the Dean Berris Show. I am your host Dean, and I'm gonna talk about today a couple of my blog posts that I posted yesterday on the C++ Soup blog, and I'm also gonna talk about a little of what I'm gonna try and do with the show as we go along. Um, First, I'm not gonna try and do a daily show. It's gonna be a little too hard for me to do that, but I'm gonna try and post videos as much as I can. So if you have any questions, or if you want me to talk about certain things, of course, if you found something about C++ that you want me to explain, I'm gonna try and introduce some more screencasts as we go along in the show. Um, so yesterday I was doing some reading and found out that, well, a while back, Intel did a simple experiment. In the 70s or 80s, they did experiments with parallel computing. So, as we all know, Intel is a chip manufacturer. They produce processors and motherboards and components for computers in general. So they're pretty much in every segment of the computer hardware industry right now. They're one of the leaders, if not the pioneer, when it comes to microprocessors, along with IBM, and of course now AMD is one of their competitors. So recently they did an experiment and sought to see if they could put more cores in one machine or in one processor than four. So because we already know that we have the Intel quad cores already available for a while already. So Core i7 came out, and you can have a quad core that had two threads per core, and that will give you, do the math, eight concurrent threads. So if you're not familiar with threads, don't worry, I'm going to be talking about them as we go along too. But Intel did a 48 core processor. Think about that. 48 cores in one chip. That means, well, they call it a cloud in a chip. So if you've heard of cloud computing before, that's where you actually have multiple machines pooled as a resource that you can use in your enterprise. Or if you've heard of Amazon's compute cloud or Google's cloud, then uh, you can imagine fitting 48 computers in a single processor. And they've managed to do it, and they're actually having more experiments done as far as that chip is concerned. Now, thinking about it a little more, if you study computer science a little, or if you're programming, in the way you do it right now or today, the predominant way of doing it is you say you tell the computer what to do step by step, one after another. That's called sequential programming. So first you do this, then you do that, then you do this, then you do that. Now, since the 90s, programmers have been spoiled by what's called the Moore's Law. Now, Dr. Moore is one of the founders of Intel, and he came up with a law. He found out that there was a law that dictated uh, the number of transistors you put in a processor, and the cost would he found out that the cost over a period of 18 months, so 1.5 years, would drop by half. So that means for the same amount of money, 18 months in the future, you can buy a processor that was twice as powerful. And this cost. Sorry about that. So this cost programmers start leveraging the processors because well, it's gonna get better anyway. So you can start writing crappy programs that were slow for this generation of the compiler, or and this generation of the processor, and then you just wait another 18 months, then it's gonna be fast again. That's because faster and faster was the deal from the 90s up to early 2000s. Now, what's happening today, sorry, is processors are having more and more cores but are not getting faster. So back then, if you could get like 3 gigahertz processors for whatever the price, now you can get 3 gigahertz processors, but two of them. Now, if you're relying on the 3 gigahertz processor becoming a 6 gigahertz processor someday, then you're out of luck, because um, the physics involved with making a 6 gigahertz processor would mean that it would need to be so power efficient and uh, so low power consuming that it and then you deal with the heat issue. So you might be needing some sort of superconductor or some kind of cryogenic um, cryogenic liquid to make sure that your the processor doesn't burn out. So that's one thing. Today processors are getting more and more cores. And if you're a programmer and you're still thinking of sequential programming, then you might be getting left behind for the next decade, because the next decade is going to be about multi-core, many-core, multi-threaded, concurrent programming. And see, the 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 theory and the concepts behind parallel computing have been around since the 70s and the 80s, thanks to research from IBM, Intel, and all the other uh, laboratories that are doing high performance and horizontally scalable computing research and development. Now, it's only recently that Intel and AMD and IBM with their IBM did the processor for PS3, which is a multi-core processor and is a real parallel computer. Now, people are starting to get these processors into their into their computers, and it's gonna be really hard for programmers to still think in sequential programming terms to leverage to use the multi-core processors. So instead of thinking about, okay, do this, do this, do this, and telling that to a computer, you need to start thinking about, okay, of all these things that can happen that needs to be done by the computer, which ones could happen at the same time. So if you're going to do a large computation, instead of doing it one step at a time, you might think about breaking that problem up and solving it in parallel. Now, it, unfortunately, when I was in college, I wasn't. It wasn't a prevalent thing, parallel computing. So I had to do my own research, and I had to pick my instructor's brains about how to, for example, leverage multiple computers in a network to solve one problem. Now, of course, my research has always been with that, and my work has pretty much been with multi-threaded programming and high-performance computing for the last 4 or 5 years. So this this isn't new to me, but the kids that are getting out of college and into the workplace, they're gonna start seeing requirements for leveraging multiple cores in the processors. So if you're programming for servers, that's almost pretty much a given nowadays, because you can't find uh, really powerful single core servers anymore, except if it's a mainframe, right? That's a different conversation altogether. But one of the things I read, so coming back to what I read, right, from the Intel Software Network, um, was that one of the one of the key problems with introducing parallel computing concepts into the computer science curriculum in particular is that the the paradigm shift between the from sequential programming to parallel programming is quite gargantuan, right? So it's like a whole big chasm in between these two extremes. So instead of thinking about the computer having just one state, or instead of thinking about the computer having only one consistent state and relying on that when you're programming, you need to start thinking about synchronizations. For example, if you have two threads running at the same time accessing the same piece of information, you're gonna have trouble if you don't synchronize how these two threads access the same resource. If you don't, for example, if you don't share information between these two threads, then that's alright. You go into message passing. So I have a lot to say about how to solve these problems and whatnot. But interestingly enough, uh, the the people in the academe keep thinking about how to introduce it into the curriculum, when in fact that will only affect the people that are still in college or getting into college. Now, my quote unquote beef with that is, how about the people that are already out there, uh, already programming, and they want to learn how to do this. How you want to learn how to program for multi-core processors and parallel computers, right? So I think Intel is doing a great job by getting involved with the university, uh, and the academia in general, um, along with IBM and all the other companies that have a stake in this multi-core business, right? So the number one problem with the current computer science curriculum, even in the Philippines, so they're having this problem in the U.S. Now here in the Philippines, we're having the same problem. First, we don't have parallel computing as an integral part of every course in the computer science curriculum, right? So you're still learning assembly, programming, and you're not thinking about, "Ooh, what if this was running on two different cores," right? You're still learning about sequential processor architectures, right? And we're not really integrating parallel computing into the subjects that matter, like introduction to computer science, right? You don't hear about parallel computing about in that setting yet. So in the next 3, 5, maybe in the next year, maybe um, we're gonna start looking at the classifieds and seeing, oh, we're gonna need people that know how to do parallel computing, concurrent programming, multi-core multi-core processor programming. Um, then we're gonna look at people trying to upgrade their skills from being a sequential programmer, even in the web, right? Even in the web arena, you're gonna start seeing programming languages like Java, Erlang, Haskell, taking a stand and saying, okay, we recognize that we need parallelism to leverage the existing processor architectures today and the ones that are coming in the future. Like, because for example, if you have 48 embedded computers in one chip, right? The programming model isn't gonna be, okay, do this, do this, do this. It's gonna be, okay, you 48 do this all at the same time, and then when you're done, give your results back to me. Or for example, you say, okay, processor 1, you talk to processor 2, and then so on, so on, so on, so on, and you basically run into a problem of, well, your workforce not being uh, up to date or knowledgeable about the about the intricacies and in the the concepts involved in making that happen, right? So, for example, what if Intel in 2010 releases a 48 core processor, makes it available for general server markets, right? So, for example, if you were running your own cloud in your enterprise using multiple machines, you can consolidate all those, right? And for example, if you have 200 machines, you just buy 5 of these processors and pretty much have your same cloud in a smaller form factor, right? And the problem then becomes, okay, so you need to upgrade your operating systems to support 48 cores. um, of course, you need lots and lots of memory. Different algorithms for efficient memory access is going to be really, really important. And then the I/O, the input-output mechanism in the computers today are pretty much going to be obsolete by the time this 48 core processor becomes more prevalent. Now, Intel is not the only one doing the multiple, really many cores in one chip play. There are others out there that are doing. I read somewhere, I'm not sure, but I'm gonna throw the link down there of people who did 100 cores in one chip. So imagine that, 100 computers in one chip, right? That is, yeah, chip. um, so that's what's gonna be interesting in the next decade. So it's gonna start today. Now, if you're already doing C++, that is a big plus for you because then you just learn how to do multiple threads in C++ and the best practices and the techniques required to better leverage and optimize for multiple core processors, right? If you're not yet learning C++, then this is a good time to start learning. And if you want to be relevant in the next 3-5 years, especially when the next version of the C++ programming language standard comes out, uh, you want to be riding that wave. You don't want to be missing the bus, quote unquote. And I'm not making it up, right? Because it's nobody's gonna see single core processors anymore. Even my Acer Aspire 1 is a dual core. It's a dual core Atom, right? But unfortunately, I can't do high resolution video with it because I'm on Linux, and right. So that's a different topic altogether. But yeah, what the overarching theme is that we need a strategy. That strategy to systematically ingrain parallel computing into the computer science curriculum and in the training programs and in the tutorials. Yeah, so if you're a person who does books or tutorials for programming languages, you might want to do sprinkling of threading or parallel processing, parallel computing, message passing um, into your materials, because that's what's going to be relevant. The next question in the next few years would be, for example, if you're doing a scripting language, right? Let's say Ruby, Python. I don't know. Name another scripting language. Uh, does your VM support multi-core, right? I'm reading that Ruby 1.9 is doing kernel threads. That's cool. Python, I don't know if they're gonna get rid of the global interpreter lock, right? When you're doing threading, things like that. Erlang is one language that embraces concurrency and supports it in the language primitives. So yes, that's cool and all, and but the question becomes, if when you really need performance, you really want to leverage the underlying machine, you don't want to be sitting on top of a virtual machine to do that. I'm gonna talk more about that in the next few episodes. Uh, basically, and I'm going to show some code. Give me some time to work on some screencasts showing, okay, how do you do threading with Erlang? How do you do threading with, no, not threading, concurrent programming with Erlang? How do you do it in C++? And maybe how do you do it with Haskell, and how you do C++. And because I am a C++ advocate, right, that's what I'm going to do. And so if you want to read more about my commentary, or if you want to continue the conversation, there's a link I'm putting down there too, or right here, depends, or both, of the link to my blog post. It's called Living in a Parallel World. It's in blog.c++-soup.com slash long slug. So yes, um, so that's one of the things. I also want to talk about quickly how I had a interesting conversation over Twitter with Zach McCormick, right? And hi, Zach. So this is the so I did a blog post too about using C++ on the web. So there was a study. Oh, there was a blog post from the Witty community, link down there, um, about Facebook using so many machines to run the website because they're using PHP and Apache for the web front end, right? Um, so I don't have anything against PHP. I have some issues with the design decisions, but I'm not going to talk about that. I'm going to talk about how if we were using a compiled programming language, and if we were using a more efficient uh, computing model for the web on the server side, we might not need to use scripting languages that consume too much resources just to get things done. So the the point of the original article or the blog post was that with Copenhagen uh, happening and whatnot, right? Facebook could have saved. It's a theoretical analysis, right? Facebook could have turned off something like 22,500 something machines if they were using C++ for the web front, and instead of PHP. And my take on it is that's a good analysis, and I'd like to see that happen. Not real soon, but maybe in the future, when especially when C++ 0x and now C++ 1x comes out. Uh, I want to see C++ playing an integral role in the majority of the web application platforms, right? So I'm not saying that just because I'm a C++ programmer, but I'm saying that because I believe that there there would be a different way, and not necessarily a better way, of doing web applications. So right now we are at the mercy of legacy with CGI and Apache and IIS and all the other current HTTP servers that were meant to serve static content uh, being retrofitted to do dynamic content. Now, that retrofitting is, uh, to say the least, is kludgy. It's a hack. Now, if we were gonna rethink how we did the web engine, the HTTP server in particular, if we because we're now living in a multi-core, see, I'm tying it together. We're living in a multi-core era, in an era where it's about concurrency, efficiency, and just using the hardware to the maximum and getting the most cost-effective solution out there, right? And yeah, so the thing is, that's why I'm doing CPP netlib. Uh, that's called a plug. um, that's why I'm doing that library, because I think th- the best way to get C++ into the web is to just start making the tools that make C++ easy to use for the web. So I'm currently implementing an HTTP 1.1 client that is doing pretty well. I'm taking some time off right now to relax and do this blogging thing, and the 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 strategy is to make C++ a viable contender for the niche where you really need performance. So if you're doing like thousands and thousands of requests per second, if you're running a website that's really, really popular, if you're doing dynamic content that needs to be really responsive, right? Um, the way I'm approaching it is I want to write tools that people would be using. So I mean, I appreciate help with that regard, and you know, I'm pretty passionate, and I'm really, really keen on seeing C++ making a mark as far as efficiency on the HTTP server side is concerned. I don't want to write another Apache, although you know, doing a good HTTP server would be a nice challenge. I love Nginx, and it's a good idea. I think it's well implemented, but let's see. I don't know what I can do yet. So stay tuned for that. I'm gonna be talking about that more in the next episodes too. What CPP netlib is and what you can do with it, and maybe do a screencast about that too. So yes. So some shoutouts. If you listened this far, thank you very much. I'd like to send a shout out to those who commented on my Facebook post. This video also went out to YouTube, Vidler, and Facebook, and to my friends who commented. Thank you very much, and I hope this one's a little better. The lighting, I hope, is better. So I'm doing this in middle of the day. Sorry, lunchtime around. Um, and I might be blabbering a little, so it's a little hard watching one person talk too much, especially about a subject like C++, right? So I'm gonna try and do it a little more layman in the next few episodes. But so yeah, please let me know what you think. Send me an email, me@deanberris.com, and you can look at the blog and comment on the articles over at blog.c++-soup.com. And so, yes, if you need to get in touch with me, here's my Facebook, here's my Twitter, and here is my website. All right. Thank you very much for watching. I'd love to hear from you. I really, really want to hear from you and your thoughts about what I've been talking about and what you'd want me to talk about. All right. Thank you very much. And this has been the second episode number 2 of the Dean Berris Show. I hope you enjoyed, and I'll see you again next time.